This is the Amp Hour podcast, recorded October 11th, 2024, episode number 679, Satellite Design Engineering with Dan Esparon from Inovor Technologies. Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Daniel Esparon, Electrical Engineering Manager at Inovor Technologies.
Hey Dan, thanks for joining us.
Oh, thanks for having me on.
No worries. I like space stuff, even though I don't know a huge amount about it. This should be interesting. What's your background and how did you get into space engineering, I guess? Is space engineering the correct term? What would you call yourself?
Yeah, I call myself an electronics engineer.
Of course.
for space systems. Yeah, it's sort of a unique challenge, but at the end of the day, what we're doing is largely similar to what everyone in embedded systems do, just with different challenges, I guess. So my background, I studied at the University of Queensland, did an electrical engineering degree and physics degree, graduated in 2018, and was looking for a graduate job.
Right.
I had an undergraduate job when I finished, so I was kind of still doing that after I went to my graduation ceremony, so I wasn't super rushed and saw that there was all this cool space stuff happening in South Australia and applied to a small company that looked interesting and got an interview and joined as an embedded software engineer, actually, to start with.
Great. And now you're the head of the engineering, the EE team?
Yeah, so I started as an embedded software engineer, spent half my time doing embedded spacecraft software, and then half my time out at Defence Science Technology Group on contract doing electronic warfare modelling and simulations. So that's kind of something that people don't really, especially like being from Queensland and not being exposed to defence that much. It's this whole science technology group down in Adelaide that is massive and doing lots of really cool work, but
I used to be involved in that way back in the day. Yep. I've been to Adelaide before because I used to work at defence companies. So yep. Spent
a bit of time doing that, but always had sort of a background in electrical and electronics. So slowly moved across to the electrical team at Inovor, and then finished up the contract and was then full time doing electronics designs for them. So then made my way through the team, and now I'm running a team of about 10 electrical engineers. And we do everything from design, manufacture, test, integrate spacecraft electronics. And
you do that all in-house in South Australia?
Yeah, so all of our design's done in South Australia. All of our, because our space systems are listed as defence dual use, all of our manufacturing is done in Australia. So we can't actually send any of our bills of materials or circuit assemblies overseas without export control.
Interesting. What about bare PCB design?
Bare boards are fine. Yep. So we get our bare boards from the US and actually from New South Wales as well. There's a company in New South Wales that make PCBs. And that's mostly for the quality side of things. So they do very high quality circuit boards.
Oh, that's not Lintech, is it?
Yeah, Lintech. So that's
of course they do all the high, very expensive. If you have to ask the price for one of their prototype boards, you probably can't afford it. So
in space terms, they're actually quite cheap. They're one of our cheapest suppliers.
Okay, right.
There you go. We have solar panels that the price of the boards on our solar panels will blow you away because they've got a custom stack up and a very special cover lay material on them. So.
So hang on. Well, let's jump straight into the solar panels, shall we? This is going to be a completely random show. So the solar panels have boards in them? How does that work?
Yeah, so we make all our own solar panels. We buy solar cells from the US, specific space solar cells that come in 27 square centimetre little cells.
Yep.
And then we have printed circuit board backing that we assemble those cells onto.
Why is that?
It's a pretty standard way of designing CubeSat solar panels. The PCB has to be particularly specific because the solar panels will cycle from about minus 70 degrees Celsius all the way up to about plus 70 degrees Celsius in the sun and do that every 90 minutes. So it's quite a thermal load on those panels. And they're also exposed to the directly to the sun, so you end up getting
Yep.
quite harsh radiation on those.
Got it. So what's the difference between a regular amorphous or silicon solar cell and a space rated one?
Yeah, so they're triple junction, so they're over 30% efficient, like spectrally efficient, that is, which is quite a bit higher than your standard silicon. So they're, I can't remember off the top of my head the exact stack up of them, but they've essentially got 3 junctions inside them, and each one is responsive in a different band, so you pick up more of the energy out of the spectrum of light.
Nice. Okay.
Yes.
And they're substantially more expensive than regular solar panels, I take it.
Oh, yes, substantially more expensive.
As well, I was just going to say, like, in terms of BOM cost, are the solar panels like an expensive part of your build, or?
Yeah, they would probably be the most expensive single item, I'd say.
Oh, really? Wow.
That we manufacture, at least. We,
Right.
when we buy components from other suppliers, they're generally more expensive. But in terms of raw cost of materials, they're definitely the most expensive.
Oh, wow. Okay. That's interesting. And I noticed that you've got, we'll talk about your payload and your CubeSat bus and everything like that, but you've got quite a few different satellites here, and I'm having a look at them, and we'll provide links down below, but they all look very similar in terms of you've got like it's like a cube. Well, it's not a cube, it's like a suitcase side, shaped thing with 2 fold out solar panels, but you've also got solar panels on the like under the solar panel arrays. Is this because of the orientation? It could be in any orientation and you still need power. Is that the reason that it's totally covered in solar panels?
Yeah, so there's kind of 2 phases. There's the initial launch and dispense of the spacecraft when we're commissioning it, and it's kind of just randomly tumbling around in space. It hasn't got active pointing control at that point.
Right.
That's something that we commission and build up that capability to make sure all our sensors and control systems are working. So, and that phase, we kind of need solar panels everywhere to just, in case we tumble into a weird attitude, we need to be able to collect power.
Got it.
Then we have our deployable panels, and what that does, it gives us, a 700 mil by 200 mil surface area on top of the spacecraft that we can point at the sun to pick up our peak power to charge our batteries and to run our payloads. But then also, we have solar panels underneath those because in some concepts of operations, we have different faces pointing the ground or the sun, or we've got a payload that we're pointing out to the moon, or different things like that. So those are generally spaced so that we can collect power when we're doing those operations.
Right, so that provides flexibility based on the mission that you've got inside the satellite, right?
Yeah,
where
that's
it
right.
needs to point and things like that. What sort of battery tech do you use in there? And I assume you fully charge it before you launch it, just in case, so you've got some initial power?
We do fully charge them before we launch, yes. They're just
Well, it sounds like a
standard-
dumb question, but I mean...
Yeah, no, we
I don't know.
probably need to cut this out, but
Right, no worries, we'll take that out. So what type of batteries does it use?
So they use lithium-ion cells, commercial available cells. That's probably all I can say about that. And we buy the cells from a company in Sydney, and then we assemble them onto battery module cards with all the cell management and protection and discharge regulators and everything.
Right, so you actually design your own BMS and everything in-house?
Correct. Yeah, everything's in-house.
Are there advantages to that rather than just... Like, I thought you'd be able to buy like a space battery solution or something.
You can. You end up spending a lot of time integrating that with your flight computer and the rest of the system, and there's sort of trade-offs that a lot of people make. So, there are companies that make subsystems, but the decision and the background of Inovor is that the CEO and founder really wanted to, design a fully integrated space solution for CubeSats, and that meant building everything. So we build everything from, we take cells, we put them onto PCBs, we build solar panels, solar regulators, maximum power point trackers, flight computers, UHF radios, the whole ADCS system, which consists of star trackers, reaction wheels, magnetorquers, sensors, everything is all designed in-house.
Wow, that is great.
Yeah.
So you provide, your company basically provides a physical satellite solution for CubeSats. Is that correct?
Yeah, correct. So we also do the integration as well. So we will take someone's payload and then build a structure for that payload, install our bus, which is what we call all the core components. We generally also design payload interface modules to provide power and comms to the payload. And then we assemble it in our clean room facilities. So we've got clean rooms in Adelaide in our office, integrate it, test it, go through the full spacecraft test campaign, environmental test campaign, and then ship it and to our launch service provider. And then we operate it as well. So we've got a full mission operations team and mission operation tool as well.
Oh, great. How many employees have you guys got? Must be a big operation.
We've got 51 people.
Oh, is that all? Okay.
That's all.
I thought it'd be more than that.
Yeah, no, it's a pretty small team, and a whole bunch of those we've kind of got two arms. There's two aspects of the business. There's the space side, and then there's also some defence consulting as well. So it's not even 50 people working on the space side. So.
Are there any, I assume there's competitors out there that have a similar sort of like CubeSat bus system. Are there?
Yeah, so if you look at Europe and the US, there's a lot of competitors there. There's not really any in Australia. There's a few companies doing space systems in Australia where they're either designing large parts of it for bespoke applications. So there's a company in Canberra who are doing air traffic communications from space, and they're building their home bus. There's a company in South Australia who's doing IoT spacecraft, and I'm sure there's some others. There's another company just up the road who are doing small sat, so 200 odd kilo space tugs. But then if you look for the people selling the buses, it's really people like GomSpace and Tyvac who are in Europe and the US, and they do essentially the same thing as us. They build all the components. They also sell their components as subsystems to universities to build their platforms, but they also do the integration side as well.
So if a university or the military or some other government organisation wants to put a satellite out there, they don't want to deal with the details of actually designing the satellite, but they want to design just the actual payload, the actual CubeSat payload. They would come to you and go, right, can you integrate this CubeSat with a satellite, please? Is that the...
Yeah, that's right. So they'll generally have they'll have a concept of why they need a space system, and we can provide the whole payload, bus, everything, or they'll come and say, we want to launch this payload. And generally it's we come with a payload and can you please put it on your bus and launch it for us that we've done so far.
Right. So what is the CubeSat bus? What does it involve? Is it like a physical connector thing with a bunch of protocols and a power budget and et cetera, et cetera? Can you explain how a CubeSat bus works? Because that's one of your company's big things, is that you have developed this bus system.
Yeah, so a bus is a term used in space to define it covers everything from CubeSats to big geos. Lockheed Martin have got geo buses that they will sell to defense and stuff like that. So the bus normally comprises of all the stuff that makes the spacecraft operate in space, but isn't the payload. So it's things like your command and control systems, all the protocols associated with that, your radios associated with that, your batteries, your solar panels, all the attitude determination control system, which does all your pointing and your attitude determination and location tracking. And then the payload sort of power management side is generally on the bus as well. And then obviously structures and solar panels and the like as well, and antennas.
So in terms of power budget, what are we looking at here? What can a small, how can you give us a physical dimension of your standard satellite arrangement? How big are we talking about?
So depending on the payload power requirements, will generally take up 100 mil by 100 mil is what our sort of form factor is, and then it expands lengthways to support more battery modules. So you can take the way the bus is designed, the way we've designed our bus is that you can plug in extra battery module cards. So each battery module is 30 or 40 watt hours, and you plug in more and more and more batteries as you require them to store more power, and then at the same time you have to put more and more solar regulator cards in to get power off the cells. So that expands up to, I think, Canini, which was the South Australian government spacecraft with a couple of payloads, that was about 2 units worth of bus. So 100 mil by 100 mil by 200 mil long worth of bus specific components. And then the rest is all payload volume. How
do you keep everything warm up there? Have you got internal heaters and stuff? Especially for the battery, I would imagine?
Yep. So yeah, you're bang on there. So the battery have got heaters. There's heaters on the batteries, but that's about it. Everything else is pretty thermally stable. It's actually surprisingly warm and quite stable once it's in orbit, because you get a little bit of heating as you go through the sun, and then a little bit of cooling, but it sort of stabilizes within half a dozen orbits of being in space.
Ah, interesting. Yeah, because I was going to ask, like, how do you actually control the temperature? How do you regulate the temperature in there? And, like, how much power does that take out of your power budget, for example?
Yeah, it's a few watts to keep the batteries warm. The bigger concern really is getting rid of heat off payloads.
I was going to ask about that. Yeah, how do you get rid of heat?
Yeah, so
because there's no air.
That's right. So a lot of thermal design, thermal straps everywhere to go from payloads to structure to heat sinks on the outside of the spacecraft.
By thermal straps, you mean thermally conductive physical copper straps or something?
Yeah, so yeah, thick copper. Normally they're copper braid, I think they are, which connects the payload sort of heatsink to the structure somewhere. And there's a whole bunch of thermal design that goes into the critical design phase that informs where they should go and what the thermal properties of the spacecraft will be. And then at the end of the assembly and integration phase, we go and spend 2 weeks doing environmental testing, which involves thermal vacuum testing of the whole system. So we cycle it up and down and check that our thermal balance matches what our thermal models say it should be.
Right. And you've got a thermal vacuum testing chamber in-house, is that right?
So we have a small one in-house. We've got a small one that we use for qualifying our sort of individual board designs. But then for a full spacecraft, we actually go to Canberra. So we fly up to Canberra with the spacecraft. For Canini in December, I had a 6-unit CubeSat on the seat next to me on the plane as I flew to Canberra with it.
Nice. I assume you had to buy an extra seat. You bought an extra seat for your satellite.
Yeah, extra seat and some paperwork to say, please don't open this at airport security. We promise it's just a spacecraft.
Do they actually believe that, or is it like some sort of official government paperwork they can't actually question, or, you can't get some dumbass security person going, no, I don't believe it, and they start ripping it open, How does that...
it is actually official, so we have to actually apply through whoever handles airport security, and we get an official piece of paper that we can show security. It says, this is what this is. We've got authority to bring it through. Please don't open it. If you do need to open it, you need to provide us with a certified clean room to inspect it in, and that kind of shuts it up.
Yes. So you're physically transporting this satellite thing on the seat next to you in the plane. Is it like in a hermetically sealed, container, or what?
It's not hermetically sealed. It's a double bagged, so it gets double bagged in our clean room in sealed bags. In ESD and clean bags, and then put into a Pelican case. Mm-hmm. Carried to Canberra, opened in their clean facilities. So that's just to maintain some level of cleanliness on it.
Right. What sort of class lean room do you need for satellite stuff? I imagine it just needs to be, reasonably clean, right? It doesn't have to be super duper.
Yeah. So
silicon wafer clean?
So the cleanliness is driven by two things. There's a requirement for it to be visibly clean for the launch service provider. So that's the people who put it on, that's SpaceX who put it on their rocket.
Oh, they've got their own requirements, do they?
Yeah, because they don't want you contaminating other payloads.
Of course, yes. Interesting.
So, but that's just visibly clean. So that's just a ISO 8 or ISO 9 clean room, which is like the lowest. That's the lowest end. But normally, what's driving the requirement is actually the optics. So when we've got electro-optic payloads, they need a lot more cleanliness. So at the moment, we have an ISO 8 clean room, a little 16 square meter ISO 8 clean room. And we've got currently a flat packed ISO 7 clean room that's about to get installed, which is 80 square meters. That's about to get installed on the second level of our office that will let us build much cleaner and much bigger spacecraft as well.
By flat pack, do you mean like IKEA type assemble yourself clean room?
No, so there's a company in Victoria who make clean rooms.
And
so they build up the whole thing in their factory in Victoria, make sure it all works together, and then they tear it all down, all the walls flat pack down, and then ship it across to us, and they're going to install it. They put it all back up and assemble it for us. So,
what's the highest profile satellite you've done? Is that the Canini one that you just launched?
Yeah, I'd say Canini is the highest profile so far. I think the Spirit team probably won't be happy with me for saying that. But,
Right, okay, yeah.
yeah, they're the two that we've launched so far. Spirit went in December last year, and Canini went on the 17th of August, 2024.
And these are all fully Australian designed and manufactured from the ground up. Is that
correct? Yep. So
right.
the Spirit was a project from the Australian Space Agency with University of Melbourne. So University of Melbourne bought the bus from us and put their payload management system. They've got that's got an Italian X-ray and gamma ray detector in it. Is like one of the primary payloads, but it also has a electrical ion thruster, which is built by another South Australian company called Neumann Space. Yeah,
Newman
that's
Space.
right. Yeah, so Newman Space make electrical ion thrusters. They were actually just up the hall from us in our office.
Okay.
And they've just moved to a bigger facility to make more thrusters.
Yeah, they were here in Sydney, weren't they? 'Cause I've actually met him once, and he was based. I think he was based here. Started here in Sydney, didn't he?
Yeah, I think Paddy Neumann studied in Sydney and then moved to to South Australia. Yep.
Where all the space action is here in Australia.
Yeah, that's right.
Yeah, right. Yeah. Is that like a South Australian government push? Is it to get to be the space hub of Australia? Is that the?
I think so. So there was the International Astronautical Conference hosted several years ago now, when Australia announced the space agency, that they were going to have their own dedicated space agency, and everything sort of congregated around Adelaide. So the space agencies here, the Inovor's here. There's there's probably half a dozen other space companies floating around the city in the Lot 14 innovation hub area. But I guess going way back, defence science technology has been based out of Edinburgh for many years. And if you look back at the 1960s, they launched RESAT-1, which was the weapons research satellite. So that was way back in 1967. They built that and launched that. So space has sort of been always big in South Australia, and defence is obviously big in South Australia, and I guess it kind of naturally conglomerated around here.
All we need is a decent launch facility. It's happening.
Yeah.
But slowly.
Yeah, we did some work with Southern Launch, who have got a launch facility over at Whalers Way, and we've done some work with them in the past. And there's obviously Gilmore up in Queensland, who are waiting to launch their rocket.
They are. That's been delayed several times, hasn't it? What's the?
Yeah, I think they're waiting on launch approval from the space agency. So.
Oh, okay. I thought there was. Okay, right. Is that all paperwork?
Yes, paperwork.
Yep. Annoying. Can you tell us more about the propulsion, the Newman's ion thruster thing? Is that just for manoeuvring the satellite? How do you rotate it? How have you got those wheels that do the physical reaction thing? How do you point and shoot?
Yeah, so I can't talk much about the Neumann thruster. I'm not a thruster expert.
That's okay.
I'm sure they would love to have. I'm sure they would love to talk to you about it, because they're a super passionate team doing really cool stuff as well. Yep. But for the Inovor bus, we make reaction wheels. So we have.
Oh, you make your own ones as well.
We make our own reaction wheels. Yeah.
Jeez, you guys aren't mucking around, are you?
No, when I say we make everything, we make everything. We make the.
Wow.
We buy motors, we buy bearings, we press bearings, we get the wheels machined, we balance the wheels, we make the motor drivers, everything in-house.
Wow. I'm impressed.
Yeah, it's a lot of work, but it's paying off, because it gives us a lot of flexibility when we're building platforms. We can build 3 reaction wheels, or we can do 4 reaction wheel, which gives us a flight spare or a redundant wheel.
Oh, okay.
Which is very useful.
Sorry, would you have to pick an orientation for that spare one? How was because you've got I assume you have 3 in 3 different orientations. If you've got a spare, how does the spare match to any of the others that fail?
You can put 4 orthogonally. Mounting them in certain orientations will give you full control with 3 out of 4.
Okay, right. Yeah, of course. Okay. Right.
Yeah, so that's how we mount them on our
got it.
bigger platforms. Yep.
Got it. And your software can just automatically take care of that if one fails. It then knows to change the algorithm to keep it pointed in the direction it wants to go, for example.
Yes. Yeah, we can tweak some parameters on orbit to address that.
Oh, okay. So it won't automatically do that? If one fails, you have to manually take over, do you? Or
I believe it's I believe it's manual.
right.
A lot of the system design is around being really stable without, when things can go wrong. The fault detection recovery is a massive part of the system design. So the sort of normal state of the spacecraft is very stable, very safe, and it lets you then, resolve issues on the ground, with plenty of time to spare.
Right.
So, you can see something's gone wrong, get all the data from it, run some tests to validate that what you're seeing is correct, and then make corrections to the control system, whatever.
What do you do in terms of how do you do the processing in this thing? What sort of core processor do you have that handles everything? And do you prefer to do it like everything modular with its own little processor, like the reaction control thing, or have its own little processor that then talks over a bus to a central one? Or do you prefer to have one central processor sort of handle everything? How modular is this thing, I guess?
So we've gone for a very modular approach. So everything is pretty self-contained with a clear comms interface to it. And then, we've got sort of pretty standard, ARM M4 processors sprinkled around the place, running the majority of stuff. And then some other sort of lower power processors and a bit more reliable processors to run our power system management as well.
When you say a bit more reliable processors compared to the ARM M4, what are you hinting at there?
They've got more flight heritage.
Okay, right.
So they've got more on-orbit flight heritage with demonstrated performance in radiation environments.
Okay, so why wouldn't you use those everywhere? Is it just a cost optimization thing?
No, it's because they just don't have the processing power of modern M4 processors or F4
Got
processors.
it. Which you'd need those for the sensor packages and all that sort of stuff, I guess.
All our flight computer, they don't have any of the encryption that we need for our radios or any of the performance we need for our attitude determination control system to run the filters and the control loops for that.
Got it. I was going to ask about the encryption side of things. So you definitely want it to be encrypted because you don't want some, nerd in his basement to take control of your satellite, right?
Yep, that's right.
Is that a requirement, or you don't have to? It's just the sensible thing to do.
Yeah, you don't have to. It's a sensible thing to do. Some of our customers require it. So for our Buccaneer May mission, which is for defence science technology, they specified an encryption requirement for that. But yeah, it's pretty standard. It's pretty sensible thing to do.
So in terms of component selection, bill of materials stuff, can your design engineers just go, oh yeah, I'll order this from DigiKey and no worries? Or does everything have to be space qualified? How does that work?
So at this point, for the CubeSats, it's pretty much you can just go to DigiKey and select what you need. We try and limit what parts we do use to a certain set. We've also done radiation testing on a bunch of parts already. So we've got data, our own data on how they perform in under total ionizing dose. Got it.
So the manufacturer doesn't give you any data on that. You just do your own testing and see what happens. Is that?
Not unless you buy qualified parts.
I'm sure you can buy it. Yes, exactly.
And qualified parts are becoming more and more available nowadays. With the big LEO constellations like Starlink and stuff, a lot of the suppliers are providing sort of, if you look back, traditionally you get a lot of the military screening options or the NASA screening options, which are like your QML standards. And they're, hermetically sealed packages.
What's a QML standard?
They define the testing flow required for a processor or a part, any part that goes into space.
Okay, gotcha.
So traditionally you go and you can buy those parts, and they're the ones that you see in the ceramic packages with big lead frames on them, and
they look so sexy. Yeah.
They do. They look they look very sexy.
It's just great, and they're $1,000 a pop. Thank you very much. Or more.
Yeah, if they were $1,000, it wouldn't be too bad.
Right.
Yeah, but now you see a lot more providers are doing, like, they call them like Leo Plus screening options, where they're very similar to their commercial automotive options, but with the enhanced wafer level traceability and sort of radiation tolerant by design, or radiation at least tested against radiation failures.
Got it. For those who don't know, LEO is low Earth orbit.
Yes.
Is that correct? Yes.
Yeah, that's where we operate.
So the higher you go, the different radiation requirements you've got, obviously, because you're outside
correct.
of our ionosphere. Is that the correct?
And the magnetic field
And the
lines
magnetic field.
affected as well.
Is there like a hard cutoff for that? How does that? I've never looked into the details, or does it just gradually attenuate as it goes out, the magnetic field? I've never really.
No, it's quite complex. There's a whole bunch of models available for modelling what your radiation environment looks like. It's kind of as you get. So in the 550 kilometre orbit, which is where we sort of have our CubeSats in, it's pretty tame. Like you sort of get a lot. You don't get a lot of the heavy ions or the heavy ion flux. But then as you go higher into sort of your medium Earth orbits, where sort of GPS is, that's a really bad belt because of the field lines up there. And then as you get towards geo, it actually reduces a little bit.
So do you have to be aware of like sunspots and all that sort of jazz? Is that like if you get a report that there's a massive flare or something, do you have to take any measures to actually protect your satellite or what?
We generally don't have to. We all get a little bit anxious when that happens. So when we had the big solar storms come through, I think it was the beginning of this year, I was personally checking the spacecraft health reports as they were coming down to see if anything was going wrong or if anything had reset or failed. But we got through that with no issues at all, which was good.
Oh, nice.
So, yeah.
Yay for our Earth's magnetic field.
That's right.
Yep,
Yeah,
solid. It'd be a bit different if you're around the moon where there's no field at all.
Yeah.
So have you done any moon, like deeper space, like higher orbit missions or anything like that? Or
No, not yet. So we've all been limited to LEO orbit so far.
So how does the comms work? I notice I'm looking at the photo of the Canini satellite, if that's how you pronounce it, and it's got like four rod antennas on the top and four on the bottom, just angled out. Are they like a quarter wavelength dipole? How does that work?
That's a little bit special, Canini, because it's got a Myriota Internet of Things payload is one of the primary payloads on that. So it's actually, there's two antenna sets, which are broken down into two elements each. So there's essentially four independent elements, which is what those rods are. So they're in pairs.
So that's not the satellite comms. That's specific for the Internet of Things payload, is it?
So 6 out of those 8 elements are for the Internet of Things payload, and 2 of those elements we get for our transmit in the telemetry and telecommand.
And so how does that Internet of Things, like, is that like a space-based Internet of Things? Someone has a gadget that talks to satellites, do they?
Yeah, so Myriota, who are a company also based in Lot 14 in Adelaide, they spun out of some research done at the universities down here. Their founders created a company, and essentially what they're doing is they've got remote sensors, very low power remote sensors that you can put out in fields or on cattle or on water tanks, and they will relay their data back via satellites.
How much power do you need to do that? What's the transmit?
So all the magic in their system is that the protocols and the waveforms are all designed around very low power transmit from the ground, and then doing a lot of processing on orbit to error correct the data back out of the noise. So I'm not quite sure what power they need, but the intent is to have them sit for years on single batteries out in fields.
Right, okay.
So super low power IoT modules.
Got it, because they're just burst in data occasionally. Is that the thing?
Correct, so they'll just burst it up when the spacecraft's overhead, and they'll pick it up and relay it back through the cloud.
So how do you receive your comms from this? Do you have your own receiver network? How does that work?
Yeah, so we have just another thing we design and manufacture is we've got a modem, a UHF modem.
Oh, wow.
So we build that, and that's on the spacecraft. We also have a corresponding rack mount unit that we've got for Canini is based out of Yass in New South Wales. So there's of all the places to have one, there's a ground station provider in Yass.
Oh, there you go.
I was there back in late July, early August. I've been in late July doing integration testing at their site. We've got a dedicated antenna there that we use for all of our command and control of the spacecraft, and that's a very low speed. So it's 9600 baud,
I was going to ask.
half duplex radio. So it's very slow, but it's very reliable. So we don't need any spacecraft pointing to make communication, to establish comms with the spacecraft, which is very important at the start. And it's a very robust link.
Right, so you can only pick it up over during part of its orbit, I would presume, or
Yeah, so we get about 4 passes a day, or 4 to 6 passes a day, depending on sort of how the phasing works. And sort of 2 in the morning, 2 at night. It's on Canini's on a what's called a sun synchronous orbit, so it passes over the equator at the same time every day, if that makes sense.
Oh, got it. Right, so you know the exact time it's coming over, and you can.
Yeah, and it's passes over the ground station almost the same time, and that's important because it's got an electro-optic payload on it, so it needs the backlit sun as it passes over South Australia to take images.
Oh, got it. Okay, interesting. So what's this other payload on that satellite? What's an electro-optical? What was it?
So it's a hyperspectral electro-optic payload.
What's a hyperspectral?
Yeah, so it's a payload. It's a European payload that was purchased by SmartSat, which are a cooperative research centre. So government-funded research organisation in South Australia.
Right.
And the hyperspectral payload, it has 45 optical bands from 400 to 1,000 nanometers, and it's got filters on. Imagine a normal
45
camera.
45 separate filters. Wow. Yeah.
Yeah, so imagine a normal camera is two-dimensional plane,
yes.
and it's got pixels all, but this has got filters on every line of pixels. So as you fly over, it establishes what's called a data cube of optical information of the ground. So it can pick up things like, you can use it to isolate, ground covers and crop crop performance. And what that lets you do is you can take that data, post-process it, isolate, which part of this field needs more fertilizer, which needs more water, what's this river system's algal bloom looking like, and that's used a lot by agriculture and sort of water management authorities to sort of inform their processes.
Right. So the company makes money by selling the data from the satellite. Is that you buy like a monthly subscription, do you, to your...
So Canini is hosting the payload, and it's a demonstration for the South Australian government on the usefulness of this data.
Okay.
So
right.
it's a tech demonstration.
It's government-funded thing. Yeah.
Correct. And there's a whole bunch of research that this has sort of spawned through the universities and through SmartSat into how we can process this data both on orbit and on the ground to get better information out of it. So
all this transmits on 400.5 megs, is that right?
No, so we've also, for the payload data, we've also got S and X-band radio as well. So for our primary command and control, it's 400 megs, but then we also have a payload data radio that's at S-band and then X-band downlink. So we don't have ground stations for that. We don't build the S-band and X-band radio. That's one thing we don't build. We buy those because they're a little bit... We're currently developing one, but that's in the pipeline. Yep. So we use a commercial ground station provider for that. We're using a provider that's got sites in Svalbard in the Arctic territories and in Troll off the coast of Antarctica. So with that, because of the orbit we're in, we get passes every 45 minutes. That's impressive. Yep. Yeah, so we get a lot of passes and very high data rate, so we can stream images down very quickly. We get low latency for the IoT payload as well. How does the launch happen? What sort of steps do you have to go through to launch on a SpaceX? You were one of how many payloads on that SpaceX launch a couple of weeks ago? How many weeks ago was it now? 4 weeks ago? Yeah, about a month ago, 17th of August. Right. It was. Yep. So we use a launch service provider out of Europe. So what they do is they take a whole bunch of 6U CubeSats and they have dispensers for them, and then they'll put our CubeSat into their dispenser, and then they'll ship that to SpaceX to integrate on the transport or any of the rideshare missions that SpaceX have. So, there was over 100 different space objects on that one transport mission. So that's everything from 1U CubeSats, 3U CubeSats. There were small sats. So small sats was kind of like 100 to 500 kilo spacecraft, all manifested by different companies, different launch service providers, space tugs, all sorts of things. And ultimately you pay per kilo, or is it per storage, meterage? This is a little bit outside of my knowledge, but I believe you pay per launch, and there's a limit on the mass you can launch with that. With our LSP, right. I think at the end of the day it is per mass, but we're not paying per 100 grams of payload mass we put on there.
So how do they actually? I've never looked into the details. How do they actually launch the CubeSat out of the the Falcon rockety thing? Is there like a spring in there that just boom, just shoots it out, or what? I mean, how does it do it?
That's exactly it. So there's a spring and a pusher plate.
There's actually a spring. I thought
they open the door and the spring pushes it out, and that separates it from the space vehicle. Yeah.
Right. So there's a little latch, and then they just release the latch, and the spring just goes boing.
Yep. That's
really?
That's pretty much it, as far as I'm aware. At least that's what the test pods look like. So yeah, very low tech, very reliable. I mean, our solar panels, you see a lot of the solar panels on CubeSats and antenna elements even. They're all the hold down release mechanisms for them are all burn wire. So you wrap a little bit of meltable wire around a resistor, heat up the resistor, melts the wire.
I've done that. I've been there, done that. Yep.
And there's a spring, and that springs it up, and that's how you deploy a solar panel or an antenna element or anything like that. So
okay, so how does your satellite know that it's just been sprung out?
Yeah, there's a requirement. You have to have separation switches, so they detect when the door's opened, they'll be released, and that's what is holding the batteries disconnected from the rest of the bus, and all the flight computers and radios turned off. Then there's a sequence after dispense where you have to wait a certain amount of time before you can deploy antennas, and then another wait before you can transmit anything as well.
Ah, interesting. Why is that? Because it might interfere with the transmitting might interfere with the other satellites that have just been launched, or what?
Yeah, that's right. They don't want you screaming out at
right.
5 watts or whatever out of your radio straight after dispense right next to someone else's sensitive receiver.
Okay, right. Is it randomized, or do you have a specific? Or it's just a separation distance, a fixed timer, like 5-10 minutes later or something.
Yeah, there's a fixed time. It's about an hour after dispense. So,
okay. An hour. Okay, right. So there's quite some actual distance separation then.
Correct.
Okay.
Yeah.
Interesting. It's just a spring, just boing, out it goes. I assume it's not fast. I mean, it's obviously travelling around the globe fast, at how many tens of thousands of kilometres an hour. But in terms of a relative velocity, from how far would you be from the vehicle like an hour after you're sprung out of it? That's a
good question. I actually don't know how far you'd be. It's not very fast. It's meters per second.
Yeah. You actually see them being deployed, and it's like it just slowly drifts out, kind of thing.
Yeah, and one of the big problems that you can have on transport missions. We were lucky this didn't happen to us. Well, not lucky. We were because we were on a dedicated band. It wasn't too much of a concern. But one problem that you see a lot on the CubeSat missions is that because there's so many objects being deployed, there's radio interference everywhere. So normally your first few passes are really poor because there's too much noise in your receiver. But we didn't have that issue. But what that leads to though is that after you're dispensed, NORAD, who's the US radar people, they will assign object numbers to every space object that's launched. So we've got a NORAD ID. I don't know what it is, but we only got that last week. So it took almost a month for them to isolate which object on their radar screen was Canini.
Wow!
And now that they've been able to do that, because it's just a big blob of metal up there, right, on their radar screens. And so they've now assigned us an ID, and they're now updating our orbital parameters every couple of days. Wow. We get a new orbital parameter set from them for our ground station tracking.
Wow! So they're tracking every little tin pot CubeSat up there, which is like thousands now, which is just...
Yeah, I was just going to look at what the NORAD ID... So we're NORAD ID 60556 is Canini, and they're just sequential. So, there's at least 60,000 items in the catalogue.
Oh, wow. So is this public? Can people track your satellite publicly? Is that the...
Yeah, I can send you some links. There's a whole bunch of websites, Celeste Track, and there's another one that's run by someone... that essentially has a list of every object that's in the NORAD catalogue and all the orbital parameters.
Wow.
And then if you go, there's an organisation called SatNogs who are like satellite radio amateur operators, and they've got a list of all the amateur or all the CubeSats and observations from their ground station antennas of
I'm
RF
on their
spectrum and
page
stuff.
now for your, so you can see the waterfall plot, and that is cool.
So yeah, they have a list of all the spacecraft too, and some details on them as well.
What is the audio? I can play audio. What is that? Is that just the audio of the waterfall thing?
Yeah, that would just probably be garbage for us because we're all digitally modulated, but a lot of them are, you can get some that are audio band modulated, or you can at least listen to the spectrum.
I just don't know how they track so many objects up there. It's just insane. It's just radar, is it? It's just they can detect things of over 5 centimeters or something.
So there's so many different ways that they track space objects. So one of the things that Inovor's doing, one of our payloads is a space domain awareness payload. So one thing that sort of defence has realised, both in the US and Australia and worldwide, is that having systems to detect and monitor space systems is very important. So there's radar systems on the ground that track objects. There's also optical telescopes on the ground that they use to monitor them. There's space-based optical telescopes, which is what our Hyperion payload is. So that's a telescope that we can use to track and detect objects in geo and cislunar space.
Oh, okay. So there's a satellite that detects other satellites.
Yeah, so we've done an engineering model of that. It doesn't quite... There are many that detect other satellites, but we haven't built one yet.
Right.
So yeah, they've got optical telescopes and they'll sit there and look out at an area of space and see things come through their field of view, and then they can calculate their orbital parameters based on how it travelled through their field of view.
How concerned are you guys and the space industry about the famous Kessler syndrome? About how if there is a space collision, then it actually generates debris, and then that just boom expands out, and then it takes out more satellites, more and more, and all of a sudden the Earth is just surrounded by garbage, and space has become completely useless.
Yeah, it's a massive concern for the whole space industry. I mean, that's a lot of the work that the Australian Space Agency are doing is on putting in the policy to make sure that there's not a lot of space debris. There's a lot of, in our design phases, there's a lot of segments of the review where it's looking at, are you going to generate space debris? Are you going to be on orbit for longer than how many years? Will you naturally decay, or are you going to stay up there? And making sure that when you launch something, once it's at end of life, that it does deorbit is quite important. And then, especially for bigger spacecraft, having propulsion to maneuver and stuff like that is important as well. So, yeah.
Right, well, I was going to ask, how long can you keep a satellite up there in terms of, trade-off with fuel?
Yeah, so our ones go up to 550 kilometres, and we expect between 3 and 5 years before they'll deorbit.
That's if you don't actually do anything.
Yeah, correct. And none of ours have got propulsion on them. They're all...
Oh, okay, right. So the ion, but you've got the Newman ion thrusters, right?
Correct. On Spirit, it has got the ion thruster, which is a demonstration of their technology. It's not on there as a actual thruster unit.
Oh, okay. Oh, right. Okay.
It's on there as a payload.
Right.
Yeah. Then once you get up to higher orbits, it then becomes sort of exponentially longer as you go higher and higher.
So all these CubeSats, I mean, they're launching thousands per year. How many would it be? 1,000 CubeSats a year. It seems like every man and his dog's putting up a CubeSat these days.
Probably hundreds per year, I'd say.
Okay.
Hundreds per year.
But it's still a lot, and do they all go into the same height orbit, or does SpaceX we'll go an extra 100, we'll go an extra 30 k's higher for this one because we'll just spread it out, and then
they all go into similar orbits on one launch.
Yeah.
They do get spaced out. How much that relates to in altitude, I'm not quite sure. Yeah, so they do get sort of spaced out a little bit, but you actually, when you look at the relative distances between space objects, it's still a long way.
It's
between
still a
objects.
long way. Yeah. Yeah, that's right.
I'm always shocked when I talk to our modelling and sim people about, how far away is that object? Oh, yeah, we're really concerned it's 5 kilometres away. And so, okay, well, yeah, that's probably concerning when you're going 7 kilometres a second. But
yes, exactly. How was the Starlink? Because how many satellites have they got up now? They have 60% of the orbiting satellites or something. I read the other day.
Yeah.
Yeah, it's enormous. How has that changed the game? Has that changed the congestion up there? Are they in their own orbital plane, or what's the...
Not really.
Have you got any insight?
A little bit. So we get notifications when there's not a possible collision, but when two objects are likely to get close together, we get a notification about that. Now, because we can't maneuver, there's not much we can do about it. So we just kind of get told.
Right.
And the Starlinks will move around, use their thrusters to move around a little bit to avoid collisions. But it hasn't really impacted us. I mean, the big impact is that you get more launches, right? So there's, with Starship coming online.
Oh, yeah, of course. So the cost comes down.
Cost of launch is falling. We're currently building our next spacecraft bus, which is, Australis, which is a, 250 kilo class spacecraft. So going from sort of 25 kilos up to 250 kilos. So they're big spacecraft with big optics. Well, bigger spacecraft with bigger optics, I'd say. They're not the biggest. Because the launch cost is coming down, it means that more and more people will be launching these small sat platforms in the future. That's really where the industry is going.
How much has SpaceX changed the industry? Would the industry be, I assume it'd be, well, it wouldn't be dead, but how would the industry be without SpaceX at the moment, who are doing 90% of launches at the moment? It's nuts.
Yeah, it'd be hard to tell. I haven't been in the space industry long enough to know what it was like when SpaceX weren't launching.
Right, you young whippersnapper.
That's right. Yeah. So, but I mean, you can just see it in there's a lot of excitement around the Starship and the mass to orbit capability of that, and what that's going to mean for the industry. You've got fleets of CubeSats launching to do things that people haven't ever thought about before. So like Myriota's IoT, you couldn't have done that in sort of old space because you could never afford to launch the dozens of spacecraft they need to provide coverage. But now you've got, miniature electronics, you've got, small spacecraft buses that are extremely capable from a power and comms point of view. You can see, nowadays you're looking at modern radios can do over gigabit per second downlinks.
Yeah.
So,
crazy.
you're streaming massive amounts of data down. The ground station providers are all over the world providing high data rate comms to space systems. So, really it's enabled a lot of these industries to grow a lot and a lot of new industry come through. And just, with more and more capacity to orbit, it's just going to get better and better.
What sort of leap would, assuming that Starship, they can eventually get it, orbiting and actually put in actual payloads out, how much does that change the game in terms of cost to orbit, roughly? Does it come down by an order of magnitude, or does it halve? Or
I've seen numbers saying that it could be an order of magnitude, at least, for Starship. I can't remember the numbers right off the top of my head, but it could be another order of magnitude drop, which would be massive for the industry.
Wow. Yeah, that's absolutely huge. Oh my goodness. What about laser comms? There's quite a few. There's a few NASA missions at the moment testing out laser comms. Is that a thing? Is that an orbit thing, or is that a deep space mission thing? Do you know anything about that? How that might?
Yeah, it's both. So there's a lot of interest in optical intersatellite links. So Starlink's using optical intersatellite links, as far as I'm aware.
Oh, that's right. Yeah, I think I heard about that. That's their new gen
one,
their new
right?
Gen so
ones.
They can talk to each other via laser. Wow.
Correct. So they got laser tracking, and that's a big area of sort of research and development, is how you get. I was just at a conference last week that had a demo of a tracking optical system where it can, it will track the object on the other side to get the link to improve the link performance. So that's really cool.
Wow, so each Starlink satellite would have to know where all the others are, and then it'd have to know its own orientation and position, and then swivel the laser pointer to point at the other satellite?
Yeah, and then we've done a whole bunch of projects with the university in the last few years on using piezo actuators to provide very high frequency stabilization on both camera images and intersatellite links as well.
Why would you need a high frequency? I mean, you're pretty stable out there in space. Why do you need any high frequency stabilization compensation?
It's to get rid of any jitter from your control system. So any high frequency jitter is the key.
Yeah, but your control system is, once you've pointed it, you only have to occasionally reorient it.
No, you have to continuously track between the two.
Oh, you have to continuously track.
So you're continuously tracking between the two objects.
Got it. So you're saying the jitter in the control loop of that thing causes a problem. So you have to go to more high frequency actuation. Is that correct? Or
no, I realised I've goofed that completely. Sorry, that was for optical imaging of the ground.
Oh, okay, right. Okay, so that's the piezoelectric stabilization. Right. So the optical payloads often need a high frequency piezoelectric actuator system.
It's an area of research to improve the performance of them, so you can get better because any jitter on orbit will lead to blurring of the pixels on the ground. So you need
blurring photos, same as our normal handheld camera.
Correct.
The image stabilization system, right?
Correct.
Okay. Wow. See, I wouldn't have thought of that, because when I think of satellite, I think of like ultra stable. It's like it's something that wouldn't have occurred to me. I think, oh yeah, they don't need any image stabilization because they've got a satellite. Sure, it's moving, but other than that, it knows exactly where it's going. There'd be no jitter in it, but the control orientation for the camera, because the camera's got to be pointed on the ground at the one spot.
That's right. Yeah,
Even though the satellite's traveling fast.
That's right.
Okay,
so you're tracking, you're slewing as you come over a point on the ground.
You're slewing,
and
right?
Any wobble in your reaction wheels or jitter in your reaction wheel speed controller will cause jitter in your image.
Of course, right. So the higher frequency orientation, higher frequency stability compensation you got, the more better.
That's correct.
Got it. Okay. So piezoelectric, how does that physically work, phically manifest itself?
You're getting to the edge of my knowledge on this.
Okay, right.
You can essentially get microelectronics. You can get micro movement from piezo stages with very micron or nanometer control, and you can drive a signal into them that will position them very accurately and very quickly as well, because they're piezo systems.
Oh wow, that is very cool. Okay, is there anything we haven't talked about in terms of the electronics systems that you want to cover? Any cool, any interesting or really difficult stuff that you've had to solve?
Lots of difficult problems to solve, but none jump out at me. I mean, the testing of these systems is really very interesting, because you do all sorts of EMI and EMC testing, which you kind of wouldn't, you don't really initially think about, but the payloads can be very sensitive to electromagnetic noise. So testing those types of things, testing those in a clean environment is very challenging. And then all the environmental testing, the vibe testing, the TVAC testing, that's all very, very cool, but that's probably another half hour worth of discussion.
Yeah, I know. No, totally. We could. Yeah, I've been involved in the vibration and environmental testing side of things. And I assume you'd have a small team dedicated to just testing?
Not really, no. All our engineers test stuff. We've got a dedicated team of systems engineers who act as test directors and test managers, and they coordinate the whole thing. But yeah, it's a lot of the engineers end up doing a lot of the testing.
And how do you break your teams up physically? Does somebody work on, right, you're the reaction control module team, you're the RF comms team, you're the processor team, you're the payload team, how does that work?
So we split by subsystems. So there's sort of the electrical power system, which is your batteries, solar panels, solar regulators. There's that attitude determination control system group, which do all your reaction wheels, your star trackers, Nadir sensors, all those types of systems, and then all the control algorithms that go along with it. Then there's the CDH team, which are command and data handling. So they do all the radio design, the link design, the command and control of the spacecraft, how protocols work inside and outside the spacecraft. And then there's the mechanical team who do the structures and the thermal analysis and all that stuff. So it's kind of split into those groups.
That makes sense.
But within the we kind of got discipline split. So there's a spacecraft software team. There's a grounds software team who do all of our mission control design and development. Then the electrical team, and within the electrical team, there's we've got a whole bunch of really good engineers across different disciplines. We've got RF engineers who are really good RF engineers, really good PCB layout engineers, power system engineers, the lot. So people have sort of got their specific area, but everyone's got pretty good breadth of knowledge because it's such an integrated system.
How long from go to woe are you talking about for a typical satellite, from when you start to when it launches?
So a Canini was announced in 2021. Yeah,
okay, that's not too bad.
And launched this year. Yeah, there's sort of 12 to 18 months is your integration and testing. So we do on the spacecraft. There's over 400 unique tests that we perform on everything from printed circuit board assemblies, so making sure the regulator works and the processor's working, all the way through to vibe and TVAC on the whole integrated system. So lots and lots of testing, and that's the bulk of the time is the test phase.
How far out do you have to book the launch? Because I know engineers do their best work under timeline pressure. If you've got no, if you've got no end date, everyone kind of, just sort of goes into cruise mode. But if you've got a fixed launch date, that kind of puts a fire up your butt.
Yeah, the fixed launch date isn't actually until very late. You can shift launches. Okay. I can't remember the exact time. It's months out. I think it's about 6 months out. You can shift the launch, but you have to book in 2 years ahead. So I think it's about
2 years ahead. Okay,
24 months to get on a launch, and then you can slip launches as you get closer as well.
Got it. So you can't launch any sooner than that.
Yeah, I mean that's something that you can, but it's more difficult.
Okay. What if you lose what if somebody loses their slot? Can somebody else come in and take their slot earlier, or how does that work?
I'm not sure, actually. I assume SpaceX manage that internally somehow.
Right. Okay. Right. Because do they have to? Well, I guess this is a special question for SpaceX. Is every CubeSat treated the same, or does SpaceX have to do anything specific for individual CubeSats, or they're all just lumps to them that they shoot out with their spring-loaded launcher thing?
There's actually SpaceX don't directly interact with the CubeSat providers. We're too small for them to. So there's actually intermediates, launch service provider intermediates.
I'm sure the larger ones they would. Yep.
Who we work with a company in the Netherlands, so they essentially we pay them to launch our spacecraft, and they put it on, they assign it to a SpaceX launch or whatever, and then they have 10 or 20 CubeSats on one transporter mission, all from different sub-customers. So
last follow-up question on the thermal side of things. Obviously you have to get the battery's important to keep thermally stable. What about all the boards, and what about the payloads and stuff like that? Do you just not bother heating those, or how does that work?
So because we're on a 90-minute orbit, so we come in and out of the sun and the shade pretty regularly. It doesn't get extremely cold inside the spacecraft. Okay,
right. What's the minimum? What's the minimum?
Around 0 degrees Celsius.
Oh wow! Oh geez, that's a piece of cake, right?
That's pretty normal.
Wow.
Payloads can get cold. So, one of the payloads we have is very thermally sensitive. Normally, the thermal is dictated by the performance of the payload. So, you've got a hyperspectral, it can't get too hot or too cold because the optic alignment can be affected by that. So,
of course,
and they'll sometimes have heaters on them, or they'll have heat sinks attached to them, and that's all down in the thermal design phase and then validated in the environmental testing.
Right, okay. And just some things love the cold of space. It depends on the payload.
Yeah, correct. That's right. Yeah, so you get like some of your infrared images, they really want to be quite cold. So you want to connect them up to heat sinks and try and get as much heat out of them. But then you have the problem of conducted heat through the structure. The rest of the structure,
so you might,
the rest of the bus will get too cold. So you kind of, there's a lot of thermal design goes into these systems to, between different heat sink compounds and heat isolation compounds and heat sink materials, putting different material finishes on the outside of the structure to get different radiative performance is a big thing that we do. So your material coating really affects how well a heat sink will work.
Yes, it does. I mean, they make heat sinks black for a reason, for example.
Yeah, and then it's not just the color; it's like the emissivity and the absorptivity as well as a problem. So you need to not absorb too much heat from the Earth or from the sun if you point that way. So
probably last question, because we've run out of time. What in terms of redundancy do you have on board, and what if you lose comms? Does the system automatically reboot, or how do you does it enter some sort of emergency mode? How do you handle that?
Yeah, we've got so we'll go into
we could do a whole episode on that, right?
Yeah, the fault detection recovery is a massive part of space systems, and the way it's designed, like the modular design is really to support that, right? So, if you have one big battery module or battery management system and you lose one critical part there, you lose your whole battery system, or you can have 5 slightly larger battery systems and you got that redundancy there. So we handle it at everywhere from the power supply level where we've got protection on all our power supplies, the module level where we've got redundant modules in the spacecraft, and then, even like file storage, we've got, a dozen different file storage locations on the spacecraft to store data or command files or things like that, or firmware images. and then the software on top of that all is managing the fault detection and recovery process as well, and logging incidents and notifying, downlinking event logs and things like that. So it's kind of a very layered approach, right? It comes all the way from the hardware level of the circuits on the board to the modules to the software to the whole system design. So,
right. And can you remote update your operating system if you need to?
Absolutely.
Well, you
Absolutely.
can, right? You wouldn't do it otherwise. Is that so? Processor versus FPGA?
We've got a lot of processors on board, and not a lot of FPGAs. But the payloads have got a lot of FPGAs because they're interfacing to different, lots of different high-speed sort of interfaces.
All right. Well, I think our amp hour's up, Dan. Thank you very much. That was incredibly interesting. I'm sure we could do an episode on just 1 hour on each individual thing we've just briefed over here.
Yeah, I think so. It's been very, very good talking to you.
It's crazy. All right. Well, thank you very much. And we'll provide links down below to Inovor. And so do you personally have any websites? Are you on the socials? Do you have a YouTube channel?
No, only on LinkedIn, unfortunately. So
LinkedIn.
Personally on LinkedIn, and you'll see updates from Inovor on LinkedIn and Twitter and all sorts. So
got it. So no one can follow you personally?
No, unfortunately, not at this point.
Social, right. No. You're not one of those social engineers?
No.
It's probably good for your mental health.
Probably.
Awesome. Well, thank you very much, Dan. This has been awesome because I'm very interested in space stuff, but, I know so little about it. So fascinating. Thank you very much for your time.
It's been great talking to you. Thanks, Dave. Thanks for your time.
All right. Catch you next time.
See ya.